Hello, this is a brief video tutorial of how to perform tests for differences in paired samples situations when we have data from subjects in two different situations. For example, a before and after a treatment or an experiment has been performed. Now, the data we're using here is people's names. So we have 10 people here. And what we have done, and we can see this in our variable view where we can see a bit more details about the variables that we've recorded, that this number before and after represents the reaction times of people to an experiment in seconds before they had coffee and then again after they had coffee. Now there is a difference between how these data are set up when we have paired samples rather than independent samples, because as always in SPSS, we need in our data view every row to be representing an individual, a subject, and every column to be representing a variable. Okay, so now even though we have reaction time in both of these variables, one of them explains or represents the reaction time before, and the other one explains the reaction time after. So each subject has contributed two values to the data set, and that's why they need to be next to each other rather than in an independent, as we would do in independent samples, underneath one another. Okay, so this is how to set up the data if you have paired samples. Okay, so what we want to find out is whether people's reaction times change through the application of coffee or through drinking coffee. And as always, when it comes to these kinds of continuous data, we need to first find out whether those data are normally distributed before we can decide whether to use a parametric test or a non-parametric test to look for differences in these measurements. Now, the parametric test that we can use in this scenario where we have two groups of paired data, so before and after, is the paired samples t-test, and the non-parametric version of that test is the Wilcoxon signed rank test. Okay, we will go through both of these, but first of all we will test whether these data are normally distributed or not. In order to do that, we go through Analyze, Descriptive Statistics, and then we go to the Explore function. Now we want both of these variables in here, okay, because we want to compare them both in the dependent list, and we want to just make sure that we have the normality plots with tests selected here, and it would also be interesting to see a histogram, but we don't really need anything else. So everything else should be deselected for this purpose, and then if we just click OK, the test will be performed. Now in this case, with the test for normality, we have two different tests here. One is called the Kolmogorov-Smirnov or KS test, and the other one is the Shapiro-Wilk. They essentially do the same thing, but the Shapiro-Wilk test is generally regarded as the more reliable one, especially when the sample size is very low, and as in this case it is with only 10 subjects. Now, as you can see, this test has been performed on both variables, before and after coffee. And in both cases, the significance value, or p-value, is over 0.05, which means in this case, actually the null hypothesis has been accepted, which says that there is no difference between the data that we've observed and a hypothetical normally distributed data set. Okay, so this data here basically is normally distributed. So that means we can perform a parametric test to compare the reaction times of people before and after they've had coffee. Now, in order to do that, and as I said, that's the paired samples t-test we'd have to perform, we'll go back into our data, and the paired sample t-test is performed through Analyze, Compare Means, and then the option Paired Samples t-test. We then simply have to make sure that both reaction time before and after are in the variables here. Now, I've done this before, hence why they're already in there, but normally this is what you would find if you do it the first time round, and we just want to make sure that both of these go into those two boxes right here. Okay, so this is what we want to compare. We have the pairs, variable 1 and 2 are the reaction times before and after individuals had coffee. And then we just click OK, And the output for this test is produced in our output window. It gives us a few sort of descriptive statistics here. We can see the means, standard deviations, and standard error of the means. So these are really, really interesting to take note of. And then also we get the paired samples test results down here. And the thing that we're most interested in this is the p-value over here, which in this case is less than 0.05. Okay, this value here is 0.001. And that is below the significance threshold, which means that this is a significant result. Okay, so we can actually reject the null hypothesis that says there is no difference in the reaction times before and after coffee, and accept the alternative that says that actually there is a difference in the reaction times of people before and after coffee. And from the actual means, we can see that there is actually a decrease in reaction time. Okay, so people are quicker on the uptake after they've had coffee, essentially. Now, the next thing we want to do is just see what would happen if we had a scenario where we had an outlier, so an extreme value that's very different to the others, which would normally mean that the data would be not normally distributed and we wouldn't be able to use this test for the data. So if we go back into our data set, all of these are relatively similar, but let's just say that one of these people, let's say this person right here, has taken way longer to react to whatever test they were exposed to than any of the others. Okay, so we will change this data to a really high value. This person, it just wasn't their day. They're really slow today. Maybe they didn't get any sleep. Okay, and their values, as you can see, are much higher than the rest. And we will see what this does to the normality tests. So we'll do exactly the same thing that we did before with this altered data, with this data that we've manipulated, which by the way is something we should never do. So this is just for demonstration purposes. We will go through descriptor statistics, back to explore. Everything should still be selected exactly the same, but obviously the data that is represented by these variables is different now. And so we hit OK, and the test should be produced again. However, this time the p-values are less than 0.05, okay, which means actually now there is a significant difference between the data that we've collected and this hypothetical normal distribution. Okay, so the data are not normally distributed, and that is signified by this significant p-value of less than 0.05. Now in this case, if we have this kind of small p-value in a normality test, we need to perform a non-parametric test in order to look for the differences between the groups. And the non-parametric equivalent of the paired samples t-test that we've just performed is the Wilcoxon signed rank test. Okay, so we will go back to our data and perform this test now. So we are back in Analyze. Then we're going to go to the non-parametric tests, the legacy dialogues, and then we want to select two related samples, okay, because that hasn't changed. We still have two related samples, which is because it's from the same people and we've tested them twice in two different circumstances, once with and once without having drunk a coffee. Okay, so we do two related samples. This looks very similar to before. We have the reaction times before and after. I've done this already, so I basically moved these over. If you saw this for the first time, this is what you would see. So you would just move these two variables over into the boxes, and then the Wilcoxon is selected already, so that's the test we want to make. We just click OK, and the output is produced. Now the difference between the Wilcoxon and the paired samples t-test is just like the difference between independent samples t-tests and Mann-Whitney, is that the t-tests use means and standard errors to compare the measurements of the two groups that you're comparing, whereas the Wilcoxon and Mann-Whitney use ranks. So that means it uses the median, interquartile range, and range, and these types of measures which actually explain or describe the rank of a value rather than its actual value, in order to compare the groups. Okay, that's the main difference, and if we remember from what we went through in the descriptive statistics lectures, is that the reason for this is that medians are much more robust to outliers. Okay, so they're not affected by outliers as much as an average would be, And that's why they are being used here in a scenario where we do have these outliers, these really unusually high or low values. In this case, a really high value because one person just took so much longer in this test. The actual test statistics, the output of the test is down here, this table right here, and what we're mainly interested in is the p-value. Okay, it's denoted here as asimp sig, so the asymptotic significance value, which is two tails. So this is the one we're interested in, and it is less than 0.05, and that means that in this case, as before, there is actually a significant difference in the reaction times of people before and after they've had coffee. So we show exactly the same thing, because if you look back at the data, even though there's this outlier, this data value which is much, much higher than the others, there is still a decrease, okay? So even Matilda's had a really bad day and she was quite slow today. She did still improve in her reaction time after having a coffee, okay? And that is the same for all of the others as well. So we still have this significant decrease in reaction time after people have had coffee, regardless of which test we've used, okay? So that was the last of the video tutorials here. If you watch the other ones, they explain how to perform similar tests, but when you have independent samples, as well as what to do with categorical data.